These are the 20 formulas. And so these are really like the way that I like to think about it is these are the only integrals that you know how to do. You only know how to do like 18 integrals, but you could be asked to do 500 different integrals. There's 500
But they
different.
would be like within these 18 parameters.
Yeah, like they're all going to somehow be related to these. Use substitution. This is something you will learn in Calc 1. So this is important to know. Let's do the integral of 2x times x squared plus 7. So in reality, there's like two different ways you could do this integral. The whole idea of a use substitution is I have those 20 formulas
Yeah.
that I know. Those are the only integrals I can do, right? So I have to write this integral in terms of one of those. I can try to do that by writing it with like a different letter. And I'm going to say that this letter is x squared plus 7 because I don't know, it's maybe a good idea. Oftentimes, it makes sense to make u equal to something that's like inside of something else.
Yeah.
So like this is literally inside a parenthesis. So that might be a good idea. Okay, so then you have to compute like the differentials. You basically do a derivative. So if you did the derivative of this, it would be 2x. And
Yeah.
then, so my goal is I want to replace the dx with
Hmm.
something involving du. That's why I'm doing this, right? I'm trying to rewrite this integral entirely in terms of u, and then hopefully it will look like one of the 18 formulas I know. So I would normally solve for dx here so that I could plug it in. You know how you would solve for dx here? You can sort of treat this like it's a fraction, right? The du dx, you can treat it like it's a fraction, although it's not technically a fraction.
Would I just treat it like algebraically in terms of this one?
Sure, yeah.
I'd multiply dx with 2x and then, yeah.
Okay,
Yeah. And then I would do du over tx. I mean, 2x.
exactly. Du over 2x equals dx. So now let's plug in to our integral. So x squared plus 7, that is u because we say so. And then dx, that is du over 2x, right?
Hmm.
Oh, look at this.
Oh, yeah. It
It
cancels out.
cancels. That's convenient. So we end up with the integral of u du. Oh yeah, I know how to integrate that. That's one of those formulas that I know. So x to the n dx, if you're integrating it, is x to the m plus 1 over m plus 1 plus c, right? So
Yeah.
in this case, and notice that in this case, by the way, this actually is really important to point out. This is an x, this is a u. They're different letters. It
Yeah.
doesn't matter though. Well, the only thing that matters is that the letter here and the letter here are the same. They have to be the same.
Okay.
And then, whatever letter that is, then that ends up being the letter here, right? It's like all these
Yeah.
letters always match up. And here,
Okay.
U's matching up. So that's good, right? But
Hmm.
those have to match up. So if you instead have like the integral of U dx, that wouldn't work.
Oh,
They
okay.
don't match up. Anyway, so what do you think the integral of this is going to be?
Okay. Then there would be a u to the power of 2 over 2.
Yeah, exactly, exactly. So we're working with u's here. The question was originally written with x's though. So yeah,
Yeah.
we should probably plug the x's back in. So if we plugged in the x's now, we would get x squared plus 7 squared over 2 plus c. And then this would be the answer. Yeah, this is the
Oh,
answer.
okay.
So we do want to plug in the x's again, but we want to do
Yeah.
that after we integrate. The whole reason why we wrote it in terms of u was so that we could actually integrate it. If you plug in the x's before you integrate it, then you're not
Oh,
going to be
okay.
able to get the integral.
So like when you're doing your integrations, like it's usually just in terms of the u, and at the end you plug in what like u was supposed to be.
Yeah, yeah. And yeah, and the
Oh,
whole
okay.
reason why we have to use this like variable during the problem is because it actually puts the integral in a form that we can actually work with,
Yeah.
right? It writes the integral in terms of an integral we know. And you could, if you want to, you can always check your results by finding the derivative of your result. I would distribute first, right? You get like 2x cubed plus 14x. And then, I mean, I think we could do this integral, right? Like this doesn't even require anything like super duper advanced. No use substitutions or anything like that. I think we just have to use the formula that we were using before.
Let's see. I would
Ever
separate the coefficients, right?
like you're talking like this, like pull it out?
Yeah. Would I like if I was yeah.
Sure. Yeah, that's what you should do if you're gonna show like every step. Then so I mean, first of all, you should probably like if you're gonna show every step, you would split this into two integrals, right? And then yeah, you would pull out the coefficient. A lot of people just don't write any of this down because they're just
Okay.
like doing it in their head. They're pulling out the coefficients in their head, I guess. Yes, you could.
Oh, okay.
What? So even when you see someone who's great at calculus, you watch your professor who's like doing integrals like this maybe on the board, and he or she is doing them really quickly, right?
Hmm.
Still, though, they have to be thinking about pulling these constants out. They're just not showing it because they're good at it and they're just doing it in their head. But yeah, if you're writing everything out, you should totally write that.
Okay. So I mean, with x3 would just be x to the power of 4 over 4,
Exactly. And then,
x to the power of 2 over 2.
yeah, x to the power of 2 over 2. All
And if I
right.
were to simplify, it would just be x to the power of 4 over 2 plus 7x squared.
Yay. I should probably make a point. What if the 2 wasn't there? What if it just was the integral of x times the integral of x squared plus 7? How would you do that? I mean, it's gonna be actually mostly the same exact process.
Okay.
U equals x squared plus 7. And when you plug in everything, you see that the x's cancel, the 2 doesn't cancel. Oh no,
Oh,
is that an issue? Is that an issue? Not really.
uh,
Is there a way maybe we can get the 2 out of the integral?
you could.
We can remove a constant multiple. So the first thing is to realize that this is the same thing as a half times
Oh,
ud.
yeah, it would just be what? Oh, okay.
So then you can put the half on the outside. And then this is the same integral we just did or whatever. It was like, what was it? U squared over 2 or something. So yeah, so then this would be your answer, right? And you could plug in the x's again, whatever. Over 2 plus c. Yeah, obviously you could like multiply the half. So this would be over 4 actually.
Okay.
Does that make sense?
Yeah, it's making sense.
Cool. Yeah, and then of course you can always check your work by finding the derivative of that, and you would get this. And it's actually worth like realizing that if you did find the derivative of this, you would have to
Hmm.
do the chain rule, right?
Yeah, you have to do the chain rule.
Because there was like an inside derivative. The inside derivative literally would be 2x, right? When you do the chain rule.
Yeah.
Yeah. So that's actually always going to happen when you have these use substitution problems. So actually, use substitution is basically the reverse of the chain rule.
Okay.
So yeah, so if you ever check your work after doing a use substitution problem, if you ever find the
Hmm.
derivative of your answer, it's always going to require the chain rule. It's kind of
Oh,
interesting. Yeah. What if I had the integral of x cubed times sine of x to the fourth dx? Any idea how to do this integral?
This is tricky.
Yeah,
Um, would I don't know, the x fourth is in brackets. Would I maybe make that the u?
probably. That's a good idea. So then we have to like figure out the d stuff. So what is the derivative here?
I would use the n plus one, right?
Yeah, yeah. Well, this is a derivative, right? We're not even doing an integral right now.
Oh, just the derivative.
I'm
Okay, that'd be 4x cubed.
Yeah, 4x cubed, and then I have to solve for dx, right? So what, like I multiply both sides by dx or something?
Yeah, so then
Right.
dx would be du over 4x cubed.
Yeah, yeah. That's the way I guess some people they don't solve for the dx. They just try
Okay.
to look at this and see if they
Mhm.
like see it in the integral or something. I don't know. I always feel like it's easier just to solve for dx. Anyway, so plug everything in. X to the fourth is u because we say so. Dx is du over 4x
Yeah.
cubed. Okay, well, some stuff cancels, which is what you always want. When you're doing a u substitution, you're hoping some stuff does cancel. X cubed
Would
start
just be, yeah,
canceling.
sine u times du over 4.
Sine u times du over 4. What now? What do we do now?
Hmm. No, yeah, you take the 1 over 4 coefficient outside.
Yeah. And then the integral of sine du, I think that's one of the 18 formulas we know. Do you remember it?
I recall seeing it, yeah, but
Was it
would
like,
just,
was it cosine? Is it
well,
derivative of cosine sine?
the derivative of cosine is minus sine.
Yeah, mine. Okay, so it's probably negative cosine.
Yeah.
Okay, so yeah, this is a fourth times negative cosine, well, negative cosine of u. Let's see. Yeah, all right. So you could plug x to the fourth in.
Yeah.
Negative fourth of cosine x to the fourth.
Let's
Dang,
see.
I guess that's the answer. Yeah, you could check
Okay.
your work by finding the derivative, of course, as I keep mentioning. Did you learn how to find the derivative of inverse trig functions? Like, did you learn like the derivative of tangent inverse of x?
We briefly touched on it, but like not for too long.
Okay, yeah, the derivative of this is like 1 over x squared plus 1, right?
Yeah.
And then so anyway, so that means that if somebody asked you what's the integral of 1 over x squared plus 1, you could say, well, this has to be tangent inverse, right? I think that was one of the formulas that was in that list of
Okay.
18.
Oh, this is just kind of thing that you just like one of those things you have to memorize.
Yeah, one of the things you have to memorize, probably. Let me ask you something different. What if it was like the integral of, I'm trying to come up with integrals off the top of my head. What if it was the integral of 4x over the square root of 3 minus x squared? Whoa, there's a lot going on here.
Yeah.
Obviously, this is not one of the 18 formulas we know, so we should
hmm
probably try to do like a u substitution here. What do you think u would be? I mean,
Uh,
there's no way you would know for sure. So like, but do you have like a guess?
the 3 minus x squared, maybe?
Yeah,
Okay.
let's try it. Let's try it. If you do the derivative of this, what is that? Negative 2x.
Yeah.
Okay, so when you solve for dx, it's like du over negative 2x. All right, so 4x over, okay, so the
Um,
square root of u, right? This is u because we say so. The
yeah.
dx is du over negative 2x. Okay, I'll just put the negative 2x here. Right, does that make sense that I put it there?
Yeah, that does make sense. Yeah.
Cool. All right, well, stuff will cancel, thankfully.
Yeah.
If it didn't cancel, we would be in trouble. So the x's go away. And
Would the -2 also cancel like with the 4?
yeah, so you have 4 over -2, which is -2, right? So, all right, I guess this is what we're integrating now.
Yeah.
So what are your thoughts here? How do you think you would approach this?
I'm guessing like with the -2, I'd move it to the outside.
Yeah, it's a constant multiple. You can move it. All right, now what about this though? Do we know how to integrate this? Is this one of the formulas we know how to integrate?
Um, Not sure.
Yeah, yeah. We do technically. If you remember your exponent rules, then yeah, we can actually integrate this because this is like we can write this with a negative exponent. Okay, wait. So first of all, a square root is an exponent, right? It's like
Yeah.
1/2 power. Okay. And we can write this with a negative exponent. We could say u to the negative 1/2 power.
Yeah.
Okay. And then this is the power rule stuff that we've been doing.
Okay.
Integral x to the n is x to the n plus 1 over n plus 1, right? That is an example. So yeah, these formulas work even when n is like a fraction, even when it's a negative number. Yeah. So what do you think the answer would be here?
Using that equation, so -1/2 plus 1, that would be -1/2 plus 2 over 2. So 1/2 over 1/2.
One
Yeah.
half over 1/2. Whoa, whoa.
Hmm.
That's crazy. All right. Can you simplify this at all? You have a half in the denominator. There's a -2 on the outside.
Um, hmm.
Yeah, this is weird. How do you explain this? How do you explain this? I guess I would start by thinking about how, okay, so a fraction is dividing, right? So I could think of this as like u to the half divided by a half. Like, I mean, it's probably been
Yeah.
since you've seen this symbol, but right, it's been a while since you've seen that. But you could technically write that if we're dividing something by a half.
Oh, then
Oh,
you're multiplying it by 2.
yeah, exactly. So I could literally say, yeah, times 2,
Oh, then it'd just be a -4.
-4 u to the half plus c, yeah.
Okay.
Yay. Of course, if you wanted to, you could write it as a square root, whatever, it doesn't matter. Last but not least, plug the x's back in.
Yeah.
3 minus x squared. Whoa. Uh, is it 3? Oh, yeah, 3.
Yeah.
All right. Yay, that's the answer. That is the answer. Oh, let's do something crazier. I don't know. Sine times cosine. Can you do this? So a lot of students think, oh, well, I know the integral of sine and the integral of cosine. I'll just do each of those individually and then multiply them, right? But that
Yeah.
doesn't work. So this
Okay.
is this is what I mean when I say that integrals can be like really hard, right? Because for derivatives, you actually had a rule that told
Yeah.
you how to find the derivative of any product. It was called a product rule conveniently. For integrals, you don't have that. So there's no like guaranteed way of solving this integral. You can, if this was a sum, then you could totally, this would be easy to do, right? Because you just integrate each thing, right? It works
Yeah.
that way when it's adding, but it doesn't work that way when it's multiplying.
Hmm.
All right, so what are we going to make u equal to? I mean, I guess there aren't too many options here.
Yeah.
I don't know what do you want to do? Make a guess.
That's tough because there's like nothing like there's not like brackets to like deal with here.
Yeah,
Hmm. X maybe?
the X won't do anything because then you're just
Yeah.
you're just switching out letters, which doesn't accomplish anything. So let's just pick something. And by the way, one of the things about doing integrals and
Yeah.
well, math in general is that at some point it really probably is just a good idea to just pick something. Um,
Okay.
rather than like just like staring at the problem for like 2 minutes and like trying to figure out what to do. At least if you're on a test, right?
Yeah.
Because I mean, integrals do definitely require you to be clever. Uh, but
Hmm.
like at the same time, being clever in math looks a lot less like, you know, being deep in thought and like staring up at the sky and stroking your beard or something. And
Yeah.
it looks a lot more like trying different things. Yeah.
Then
Anyway,
I
yeah,
guess d of x maybe. No, I mean dx, not d of x.
you can't really do that. You should when you look at the integral, you should like pretend the d of x isn't even there. Just like
Okay.
just integrating that stuff. I don't know. The dx is there just to kind of let you know that like you're integrating with respect to this letter. It lets you know that that's that letter is going to be in your final answer.
Okay.
However, if you went with sine, it would work. And if you went with cosine, it would work. I think,
Also, either of them would have worked.
but all right. So the derivative of this is cosine, right? So if I solve for dx, I get du over cosine. See, so
Yeah.
yeah, it does. Things do actually end up working because things cancel. So
Okay.
sine is u, and then cosine x, and then dx is that.
Yeah.
Yeah, things cancel. Cosines go away. Cool. Integral of u dx. What is the integral of u dx? Like u to
Hmm.
1 power. Once again, this is the formula, right?
Yeah.
So yeah, what is the integral of u?
Well, it would be since it's u to the power of one, it'd be u to the power of two over two.
Yay. U to the power 2 over 2. So sine squared of u over 2
Yeah.
plus b. That works. That's the answer.
Wouldn't it be a sine squared x?
Sine squared x. Yeah. Sine squared x. Good catch. I would lose a point or two on a test for making that mistake. Oh no. Let's try u equals cosine x just to make a point. I'm only doing this to make a point. So dx is du over negative sine of x. Plug
Yeah.
everything, and so u is cos. So replace cosine with u.
Hmm.
Sine du over negative sine x. Sines cancel, I guess. So it's an integral of
But you're
negative
left with the
u
negative. Yeah.
du. Yeah.
You take the negative out then.
So it's like very similar integral to what we just did.
Yeah.
So u squared, so like negative u squared. And the interesting thing here is that u is different. So when I plug u in, I get negative cosine squared x
Hmm.
over 2 plus c, right?
Yeah.
Wait, what? That's weird. I'll
Yeah, I
make this
gave
a
different
little bit
answers.
neater. But th- they're different.
Yeah,
How do we have two different answers to the same question? That's
that's
really
strange.
weird. Yeah. So the actual reason why they're different is because they're not actually different. Or they
Oh,
are different when you take into account the fact that there's a plus C here. So like they're supposed to
okay.
be, like yes, this stuff is different, right? The stuff that isn't the plus C, but they only
Yeah,
differ by a constant. And you could use trig identities if you want to. You don't have, I mean, there's no reason really to, like, you're not expected to be able to do this. But you could use trig identities to show that these only differ by a constant. So
Okay.
they actually are like you know, really close to each other. And then when you take into account the plus C, then they actually become like literally the same. They could be literally the same. Um,
No.
Also, you could just take the derivative of each of these, take the derivative of that, uh,
Yeah.
take the derivative of this, and you would see that you get the
The
same
same expression.
expression. So you can have, yeah, you can have expressions that look different, but you take the derivative and they get you the same expression. So, yeah.